AI is figuratively taking over the world, and soon enough, it might actually take over the world. Just kidding with that. But today, I'm going to show you how you can make your own simple AI, and it's going to be really cool, all in Python. I'm going to explain it to y'all to where y'all can understand it. And now, this video is probably going to be a decently long video, like maybe an hour. I don't know. Check how long the video is. But I might not even record this in one sit down session. So just know that you do not have to finish this tutorial in one session. Like, you can spread this out over multiple days and just do whatever you like. I mean, if you're like you already know a little bit about AI and a little bit about Python and coding, you can probably skip through this video rather quickly if you just want to get this thing working. It's not the most complicated thing, but it is pretty cool. You see, I have VS Code open. I have this little drawing extension, so I'll be trying to explain stuff in here. I have a transcript where I'm going to be taking the code, because I've already coded this up. I'm going to put it in here. Y'all can't see it, but I'll be able to see it to make sure that this entire thing runs smoothly. And yeah, so let's just get into it. I'll explain a little background behind this project. So this is my little folders that I have over here. I call it the neural networks. That's my folder. And we go into built networks. You can just focus on this thing, this monstrosity. This is neuralib.py. This is the brain dump of how I made this. It's perfectly functional. It works. 330 lines. Before you click off the video, I have this other file called simplified lib. It's much more compact, much simpler, only 210 lines of code. It functions the same, but I removed most of the comments. So you have the different sections, which is what I'm going to be dividing this video up into, 3 different sections. And yeah, this is going to be what we are going to be making today. And I think it's cool. It's not a powerful AI. It's not going to be your ChatGPT, and it likely won't be reasonable to use for many projects. But I mean, if you do want to create something and you don't know how to solve a problem, I guess you could try to make this work, because it does implement something where you can save networks. I don't have anything saved right now, but nothing saved. But you could save different networks using Pickle. Pickle is pretty cool. Anyways, I'm just going to copy this over to my little transcript thing. That way we can make this whole thing from scratch, which I'll show a screenshot of it. It's a pretty cool program that I wrote in Python. And using OBS, I can record just VS Code and not my transcript. So I thought that was pretty neat. Anyways, I can just go over the outline of this, like actually in here. I don't think I need to start typing it out yet. It's going to be a framework. We're going to define some classes, a node class, a C node class, and then the actual network itself, which is very modular, very functional in the way that it calls a lot of its own functions. And this actually can be imported as a library, which is what I'm going to show you. I'm going to show you all that this stuff works. Believe in test. Should I go is the main thing that I use to test on my network. And basically, you have some imports. These are just like boring imports. We import the simplified lib. This also works on the neural lib, because they're technically, with a little bit of changes, they're the same program. And then to get this to work, you define a net. And now this is going to be the sequence of nodes, which I'll explain later. It's going to be the sequence of nodes in each layer. So you have a 3-node layer, 4-node, 4-node, 2 nodes, 3 nodes input, 2 nodes output, and it goes all into the network. And so you define the network as a neural net of the net. And then I'm going to randomize it, which is another function defined for the network. So this one's defined in the network. which essentially sets all these values randomly. So once again, I'm going to need to draw a diagram for all of this. And then we start making sense of all the data. So this is basically a stoplight logic type of thing, which, I mean, you can already see. It's really simple. I don't need all this massive network. I'm actually going to drop it down to 2, a 3, 2, 2. At the end of the video, or actually, I'll show you both ways. I can actually drop it down to a 3, 2, but I'm gonna add the 2 in there to show y'all some of the nodes in between and how that stuff works. Anyways, we initialize the names, which is gonna correspond to all of this mess down here, which is where we see that I actually want put in before put out. Where we see we have list of tuples, which don't mean anything until you look at the out name. So this, for each index in this list, it corresponds to the other tuple. So this is the input, and this is the expected output. This is the input, this is the expected output. So if we get a green, then the expected output should be to go. I mean, that makes sense, right? Can't type today. If we get orange, the expected output should be to stop. Yeah, don't know what I did here. I think I just fixed a bug. But yeah, this should be the only one we find. I've tested this before, it works. So even if the logic was messed up, like, the program was still working. And anyways, you initialize the names, and then, so this is the data set, basically, that we're going to be running this on. If you have some other data, you can create functions that'll convert your data into the format required. And then we're just going to test it, which will print out a report going through all of the put in, put outs, and tell you if, is it getting it right or wrong. So we're going to test it. We'll sleep, which just waits. And then we're going to random learn, which random learn will print out all of the knowledge it's gaining. You'll be able to see it. You might not be able to see it for this one because it's kind of fast, but sometimes you'll be able to see it turning from red to green because I have everything colored. So it'll turn, the colors will turn from red, meaning it's testing, getting stuff wrong, to green, meaning it's testing, getting stuff right. And we'll do a final test, which will show y'all the network works. So that's pretty cool. I'll sleep a little bit more, and then I'll do a P-show, which is kind of goofy. It basically just gonna pretty show. That's what it stands for, pretty show. And it shows all the necessary data for the network. And I'll actually do this later, but I can network dots show, and that's pretty ugly. It will literally print out the repler, which is a function you can define for classes in Python. So basically, whenever you print out, you say, I want to print out node, it'll print out whatever the repler is. I'm probably saying that wrong. It probably stands for something. I don't know what it stands for. But anyways, that's a bunch of mess. And we're just going to run through all this and see how it goes, That way y'all can better understand it, because it's really important that you understand the network. You're not going to be able to just go and build one. I spent about a month trying to figure all this out. Like, now it seems kind of obvious. I mean, that's the only reason why I'm able to make this video, is because I think I'm pretty much got all this stuff down pat. I guess this would be a good time to explain what a neural network is. So let's go over to the free draw. I'll bring this over a little bit, and we'll hide the bottom. So in a neural network, our neural network in particular, we have a couple of layers. Well, circles, So we have this one layer, which is going to be the input layer, the 60 inputs. We have a hidden layer, and now this is the actual name for it, and an output layer. Since this is any layer that isn't the input or the output layer is considered hidden, which is why I called these nodes C nodes. And these things have unique properties in the way that they are initialized, and I have to make exceptions throughout the code for them, which is a shame, but I separate them from nodes by extending the node class and adding their names, which just makes everything a little bit more readable. But anyways, the main parts of a neural network is that you have weights, which a weight will have a value, and then you have a bias, which will also have a value. And we're gonna have to go through the input, hidden, and output layers, layers, because these are called layers, separately because they all work separately. So this one will have no parents, it will have children, and it will have a bias of none. I set the bias to be none because the input biases are actually determined, the activation isn't determined by biases, but rather the inputs. So there's no need for a bias because the inputs determine that. Now, whenever I say children, whenever you see the list of children, that is rather the list of children weights. It's not the list of the direct nodes. That would be easier and probably possibly more efficient. But then again, there's a lot of stuff that could have been done more efficient for this project. But anyways, so you have the weights, and whatever goes into here, let's say it's a 0.5. It'll go through, multiply times the weight to this node. And so you end up getting 0.5. However, the activation then goes through this bias for the node, which the hidden layer will have a bias. And so -1 will turn that 0.5, why did I choose 0.5, into, that's a point, -0.5. And that'll be the activation for this node. So you can imagine that this is kind of a grayish node. Then we get into this mess. So they will have parents, they won't have children, and they also won't have a bias. Because what we're going to do for this is the sigmoid function. The sigmoid function is kind of cool. It basically takes a value and it's going to place it between 0 and 1, which is really useful because it simplifies the data. It doesn't make the network work too hard, and trust me, if you want the network to produce exact numbers, like, you might be better off doing it with the sigmoid function and converting binary. Like, I am no expert in this, but I have had a lot of trouble trying to do anything except for a sigmoid. And now there are tons of different functions like this. I'm not sure, but like, we'll figure it out later on in the code. But whenever we're calculating some other stuff, it might use the sigmoid function as well. Like, the biases might be sigmoided. The weights are not sigmoided, but there are tons of different ways you can do it. That is partially why NeuralLib, my original thing, is so much more extreme. You have a leaky ReLU, a normal, a ReLU. Like, you don't have to worry about what all these mean. That's why I removed it. Don't worry about it. Anyway, so this will produce the outputs between 0 and 1, and whenever your inputs are between 0 and 1, this makes it, like, just really easy. And so it won't have any, sigmoid is basically gonna produce the outputs. And I also have it to where if some bizarre number gets produced, like -700, I believe is, I don't know why I said this as the limit, but that is the limit. -700, it'll round to 0. because it creates some like overflows and stuff. So, problems you have with AI. Low level languages are definitely easier for this. But to explain it to y'all, I'm glad I'm using, all this Python nonsense. Python is my preferred language. So, yeah, and it's easier to read, understand. And you should notice that Python is commonly used in AI, but because it's easy to read and built on a low level language such as C, so any libraries that are in Python that use AI are built off of low level languages and not actually built in Python. So if you want to make it from scratch and make it actual efficient, which I have no business doing. My computer, I love it, but it's nowhere near powerful enough to run a decent AI. So I'm not going to bother with that. But if you have a powerful computer, go ahead. Go do that. If you got the storage, might as well download stuff online, but have fun with that. Anyways, let's get to the outputs. I think I'm going to have to run this again. Come on. There you go. So Python should I go.py. There we go. Now it's colorful. Yeah, I guess the biases are initialized to 0. The biases being 0.01 might be a leaky thing. And then the output, you can see, finally, we have time to look at this. The children, so the weights, kind of cool. Biases, kind of cool. But in the end, the final output is determined by the sigmoid. So the negative 4.2 will multiply times its activation, then go into the sigmoid to produce, the final output. Well, let's look at, actually, I was going to say let's look at this, but I'm actually going to set this to a 3-2, because you can really see what's going on once you got a 3-2. So, node 1, we can actually look at the weights here. We can see that this is probably green. This is, or no, so this corresponds to this. This corresponds to this. So it's kind of matrixy. There's a lot of, if there's one math concept that you should learn for programming, it's matrices. They appear everywhere, whether it's AI, 3D, learn about matrices. Anyways, so that corresponds to all that nonsense. So you'll notice that if you get a green light, then you're going to end up feeding 5 into node 1. You're going to end up feeding negative 5 into node 2, which is stop. So it's going to say, no, you don't have to stop. Yes, you can go. That's what it's going to be saying. And then if it's orange, which node 2 corresponds to orange, you can look up here. Node 2 is orange. Node 3 is red. They each have similar negative values and similar positive values. And so this negative corresponds to the node 1 of layer 2, the output, which corresponds to go, which means that it's going to produce don't go, a 0 for the go, which is exactly what you want. And then the positive values shared across both of them will produce a positive value for the stop, which is good. So yeah, neural networks are cool. Whenever you get into large language models and more complicated stuff, this stuff gets insanely hard. So while it's easy, try your best to grasp the concepts, but don't feel bad if you're getting left behind. I kind of wish I had a tutorial like this to watch, and I didn't just try to do this by myself, because I had to look so much stuff up, like why isn't this working? And I had to trace through, like y'all saw this mess. I had to go through all of this nonsense that I barely understood just to try to understand it. Okay, so now that we have everything explained, hopefully you understand kind of what, networks work, how AI works. regardless, it's time that we actually get into coding, which is what y'all are here for. So I'll create a new file, and it's gonna be video lib dot py. All right, and we're gonna import some stuff. Now I stick by my claim that we're making this from scratch, because the AI part is absolutely being made from scratch, but we do have some imports. So from random, we import randint, which this is one of Python's base libraries, which means that we don't do anything, like it's built into Python. Another one built into Python is math. And now I feel like both of these, you can't really say like it takes away this AI being made from scratch, because it's basically in the language. I don't know why they didn't just build it in and you have to import it, but regardless, we're also going to import pickle, which I love pickle for a couple of reasons. It makes storing stuff easy. I mean, that's about it. It makes storing stuff ridiculously easy. Like, I can store a Python list, which is a list of items. I can store that using pickle, and then I can read it, and it just creates a .pickle file. It just makes stuff super easy. And then for, just to make everything pretty and a little bit more readable, I import colored from term color. Nope, I did not spell that right. There we go. Yeah, that just makes stuff a lot easier to read. I mean, you can see it down here. Like, I have the yellow. I mean, you can read this a lot better since I use the colors. Yeah. And now we finally get to sections. Section 1 is what I'm going to call the framework, and this is going to be the class for the node and the C node, which is, what everything's based off of. Alright, and now this is going to be the first part where I get into some of the Python, stuff. So, this is a class, and we're going to call it a class node. And you're going to find these through a lot of programming languages. This program was my first experience with the class, and it definitely makes stuff a whole lot easier, because if you go through all the data that a class node is going to have, all the functions that it has, and if you were to not use a class, you need to store all of this in your own sketchy list or, tuple. I guess you could use a dictionary, but using classes, it makes it a whole lot easier. And for every class, you're going to want to define an init, which is basically going to be where we create the node. So we're going to say like n equals node of I don't know, 1, 2. Like, you're going to pass in some arguments, create the node, initialize it. That's what the init is going to do. And we're going to take a couple of inputs, parents, bias, and children, which is the main things. If you go back to our P show, that's the important stuff that I actually show. And so we'll initialize a whole lot of stuff. We set self.parents equals parents, self.bias equals the bias, the children equals the children, and then we're going to also initialize a couple of extra stuff. So we have a value which should be at 0. We're going to have a derivative which is going to be at 0. And all of these are going to be used later, so they'll be explained. Error equals 0. I'll separate these. I'm not initializing some of them. I'll separate these because these are going to be explained whenever we get to them. And now this has to do with the back propagation and propagation that I believe I already talked about. And then we're going to have new parents, which is basically my janky way of changing the children and the parents and keeping everything the same, because you can like kind of track it, switching the children. It's weird. It's dealing with arrays, but if you do it the right way, it's gonna work. You're gonna have to trust me on that. There's definitely better ways to do it, but this is how I found it. I feel like if you use pointers, or maybe if I used more classes, I maybe could have made it better. But this is for keeping track of stuff and ensuring that I can change the weights properly. Anyways, there's another unique function besides the init function, and you're going to see that these, kind of weird things are going to be initialized with the double underscore. And I'm actually going to collapse this. Just makes it a little bit easier. Actually, I don't know why I'm collapsing it. Let me just remove the bottom. Okay. So, Ripper. I don't know how you're supposed to say that. I don't even know what I say. Anyways, this is going to be what you would call if you said n equals node of, like whatever. And then you print node, rather than printing the location of the object, it's going to actually print whatever we define here in Repler, which makes it easy for, easy stuff. And this is a little bit of a weird thing. We're going to define a function which we're going to call round 2, I guess. I don't know. You really don't need to. I'll put lambda of x. And now lambda functions are weird. I don't like them. They show up everywhere though. So basically, take in the x, and the x that comes out is going to be round 2, which is a function built into Python. So now this is a mouthful. I don't like the way that I ended up doing this, but what this is going to do is it defines a lambda function, which means that it's got an x, and we're going to round x to the second decimal, so like 0.00, if x is a float. Otherwise, if x is a list, we're going to round 2 for every object in that list. Otherwise, we're just returning x, and we're not going to mess with it anymore. What we then do is we actually return what we're going to print. So return an f string, which an f string, for those of y'all who don't know, is a string where you can use curly braces to include variables. So we can include r2, self.parents, and then we go outside of our concatenation. I think that's how you say it. We do children. It's going to be r2 of self.children, comma, the bias is going to be, I guess I would prefer a space there, or just something uniform. Bias is going to be r2 of self.bias. You will notice in this code, I'm very bad at staying consistent with the way I format things, which is why this function is the mess that it is, but I don't believe I used that anywhere else. We're gonna define another function that I just call data. That's a bad name for it. This is gonna return a different little bunch of gibberish. You can copy it down if you would like, but it's just an f string of all the detailed gibberish. So I just copied it down. Luckily, I can copy and paste things, which should speed up this video. So I hope y'all are happy and I'm able to do that. But if you want to just look at it, this is everything that it is. I guess I spelled, I didn't include new children. There we go. So yeah, P, error, bias, children, value, derivative, gradient, new parents, new children. And that's all data does. These are used in two functions, which you have the option of omitting from your program. This one is used in pshow, and this one is used in show. So show, I primarily used for debugging, because like error and the bias, if I want to know everything's working, that stuff is a little bit important to me. pshow just shows you the network, and you can actually, I already showed you before, gain insights as to what the AI is doing, especially for simple, really simple things, AIs. Okay, so we're gonna into a couple of like actual functions that do stuff. We're gonna get a assign. Now we're gonna have an assign, and then we're also gonna have a sig assign. Now assign is going to be for input nodes, and then sig assign is gonna be for literally anything else. So assign is a little bit different from sig assign. They both take in self and value. Sig assign, or normal assign, sets self dot value equal to value, and sig assign is going to do something similar. It takes in self value, it's going to assign that, but since it's not an input node, it's going to go through back propagation, which means that it needs a derivative, which is basically how impactful was it. Well, you'll see more about that later. We're going to set the derivative to value times 1 minus value. And so you can like plug in and check, see what's gonna pop out. If you have a 0, it's gonna be 0. If you have a 1, it's gonna be 0. But if you have anything else, it's gonna be an actual number. And once again, like all this, it's gonna make more sense once we get into the propagation and defining those actual functions. I'm just trying to give y'all a brief overview of everything. Anyways, in the next function, this is definitely used in backpropagation. Hide, and once again, very bad names. There must have been some terminology that made me use these names, but this sets the error equal to hidden. This is definitely used in backpropagation. And then it says the gradient, which, by the way, I'm not sure error ever actually gets used. I believe that's just for printing purposes, because what we really need is the gradient, because the gradient tells us how impactful it is. So you find the error, you multiply it by the derivative. Alright, and we finally have fix. It's going to be the start of a long line of passing on data, because it takes in learning. And I'm hoping I'm not going to break it by doing this. I forgot to name it. It's called fix. I believe I won't break my program by doing this, but I initially had a whole lot of functions that use this value, and I would set it to a default. I believe I've made it to where the first function has a default, and so this shouldn't need a default, which, by the way, if you're new to Python, you can give anything a default value, and if this isn't passed in, then it'll simply be the default value. So in the fix function, we are going to fix all of our things. So we've gone through the forward propagation, gotten the output, we've back propagated, calculated the errors using the hide function. So fix is then going to update all the weights, update the bias. Alright, so we do parents equals self.new parents, and then we empty new parents, Then we're going to say self.children equals self.new children. And then we're going to clear self.new children. And then we're finally going to check if self.bias is not none, which I call this to show you that bias is in fact none in our input layer, but for any other layer it is fine. So the output layer has a bias, and any layer in between that would also have a bias. So if bias is not none, then we're going to set self.bias minus equals, which minus equals is Python's cool little way of saying equals self.bias minus, which I love it. And if you're used any other programming languages, they might have something like this, minus minus, which would be -1 or minus equals 1, and especially plus plus, which is equal to plus equals 1, because for most programming languages you can do something like divided by equals, you can do something like times equals, you can do mod equals. Anyways, if minus equals learning, which is the rate at which stuff is supposed to change, so self.bias minus equals learning times self.gradient, which we had already calculated. Okay, so this is our little node class. You can see that there are some things in here that probably should be in C node, but C node actually is more of a, for convenience purposes, is why we have it. And so by passing in node to C node, the C node will inherit from node. So what we're going to do is we're going to define another init function, because this also needs to have an init, unless we would like it to take everything directly from the node, which it won't, because it's going to have some other stuff. We set self, or we take in, actually, how about I copy some of this? We're going to define init, takes in self, parents, bias, children, and then we're going to super dot init. It's a super init function. The parents, bias, children, and all we're going to do is set one value, self.name equals none, because in should I go, you'll see that we actually create our network right here, we randomize it, and then we initialize the names after we've already created everything. So we already have the C node created whenever we actually give it its name. So if I don't initialize the name, it'll print none, which is, it's pretty useful if you care about all this pretty stuff like I do. And so the repler is going to be super, which basically just means it just takes what is already there, and it just adds some other stuff to it. So whenever we repler the C node, we are going to return super.repler. We hashtag it to make everything so pretty, and it prints the name colored, the self.name, into light yellow, and the data, it returns super.data with an extra thing for n as the name, just to include it. I mean, you don't really need that in the data. And then we'll define one little silly function, which you need, or you don't really necessarily need it, but it makes stuff easier. You could just go in n equals node, I know I didn't type that right, and you could go n dot name equals blah blah blah, but I just like functions, I guess. I don't know why I didn't simplify that whenever I could. And I believe this is all functioning. We have the scene node, the class node. I would like to say congratulations, you have created the framework, I guess. Now section 2, which is where we at the section 2, we're going to create the network. So we created all the nodes, we have the classes for them. Now we're going to create a class for the neural network that engulfs all of these nodes. And we're going to initialize the names. So the names, we're going to initialize the, kind of framework in which it's operating. So are we going to have 2 input nodes, or maybe we're going to have 3 and 16 different layers until we get 1 output? Like, what all are we going to do? Yeah, that's what this entire thing is going to be. And we're also going to handle, I believe, some of the prettying. So we're going to handle out all the printing in the terminal in this, because, the node printing, we're going to add that to our neural network. That way we can print out our neural network. Now, it's not going to work in the same way that the other one did. I should have absolutely made it to where it could have. Improvements. I can make a video improving my neural network if y'all want. These are definitely all improvements that I can make. And also, it uses Pickle, which I've used this a couple of times, and it works. It's really cool. And I can just literally dump my neural network into some file somewhere, and then I can just reload it and keep training it. Now, my networks are nowhere near advanced enough to where I would need to do that. Like I showed you once again in the intro to the video, it takes like 3 seconds to maybe less. But definitely if you made something more advanced, you would need this. And that is going to be, well, we're going to set up the network. So we already have 2 classes, and the next bit of everything is going to be in our neural network class. So we'll define an init. It's not as advanced as the node. You just take self in the param, then we set self.param equals param. And to actually end up initializing everything, we need to randomize, which randomize is it'll actually start putting in data for the parameters. So we're going to take a self, an init that equals random. We're going to have a high and a low value, which is we're going to initialize all the weights or biases, initialize everything, and we're going to select random stuff between 1 and -1, which is what I would recommend. I mean, you don't need to randomize it that much. You don't want to set everything to 0, because then nothing would happen, because zero's a problem. But you don't really need that much randomness, So in randomize, we set self.times equals the length of self.param. And so we're going to be able to iterate self.times over each thing in self.params, because params is going to be a list of number of nodes per layer. So we're also going to set self.data equals array. And now we're going to use data a whole lot, because data is going to have all our nodes. So very important that you randomize. If you don't randomize, then your entire thing is going to break. I can go to should I go, and if I don't randomize it, so all should break. So let's see, Python should I go? Yep, we don't have any data. Now this is a little bit of a bad design, but definitely randomize it. You want to randomize everything. That way you have stuff, the data, and I can probably remove the bottom thing. So if init.lower equals random, because there are other ways to randomize stuff. For example, he or he randomization is one way that I had implemented, but I removed to simplify this. Then we're going to self.data, and we're going to append, which for those of y'all who don't know, appending would just add something to a list. So it adds it to the end of the list. So we're going to append a list of scene node of none bias. It's going to have no parents, I believe, and then it's going to have a rand int of low and high. And now we're going to do this for underscore in range self.param of 1. And what this is going to do is it's going to create a list of integers, which are the weights. So these are going to be the weights of, if you go to scene node, it shows you the children. So we're going to create that for the range of the next value, because the amount of children that it's going to have is going to be whatever the next layer is. And now we're going to do this. It's getting a little messy, I know. For underscore in range self.param of 0. Alright, so that is a handful. I'm going to go over this again. We're going to add a C node, and C nodes have no bias. They have no parents, because this is the input, by the way. Output C nodes are handled a little differently. I could have created separate classes for those. It's a random int, low, high, and these are going to be the weights, and it's going to be random weights for all the children that it's going to have, which is going to be in 1, because Python's weird. Indexes start at 0 actually, so 1 would be the next one. And we're going to do this for the range of parameters in 0. So we're going to create that many C nodes. So make sure you know the difference between what's going on here and here. And it'll look like they're the exact same. They're doing different things. So now what we're going to do is we're going to for layer in range of 1 to self.times -1. Should be parentheses around that, because the 0, we have to specialize or just specify that it starts at 1, because we've already done 1, and we have to specify that it ends before -1, because we want to do the output separately. And so for each layer, we're going to self.data.append, and now this one's going to be a regular node. Now this works, trust me. I can go over this real quick. We're creating a node, and we're going to define the node's parents as the children from the previous, and we're going to do this for each normal node. So for each normal node layer, we're going to do this. And then we're going to set the bias to 0, because we don't need to randomize that. We're going to randomize all of the children, because we don't have parents to base all that off of. And it's going to keep on iterating down. And then finally, we're going to do something custom for the next little section, where we're going to self.data. I should, in fact, properly define all this. Self.data.append a C node of node.children. So we're going to have to do this again. this whole nonsense. For node and self dot data -1, which just goes to the end of the list, and 0.001. This is really important, because if I set this to 0, then it won't return anything from the gradients. So very important that you have at least something leaky right here. And this is going to be for underscore in range self.param of -1, which is again just at the end. Alright, boom. I can go over this one more time because it is a bit confusing, and that should organize it a bit better. So we'll look at this second thing. This is for underscore in range self.param 0. This one is going over each next layer. This one is going over the last layer, which is what this -1 does. It's the last layer. And so for this, it doesn't need, C nodes are, yeah. Okay, so they're in the same order. So this does not need a parent, does not need a bias, creates random children. Everything needs random children. This needs random children. This doesn't need a bias, and then it needs to get the parents from what we already just did. And this one needs to get the parents, doesn't need children, and it needs a leaky bias. And that is how we're going to do it. And if we get anything other than random, which I spelled wrong, then we're going to want to raise just a simple value error, colored. We're going to make it red, invalid, type init. And I actually might create something that will prevent this whole fiasco when we init the names. That way, you know, we have data. So if there isn't data, I will add that. So we'll actively add that as we go on and do the next couple of parts. But I think for the day, I'm going to log off. Alright, I'm back, and I think we've gone through most of the fundamentals of what we're building, you know, this little mini application. But before I continue, I actually want to propose that in the init function, or, you know, the function of the class, we call self.randomize. And now this will prevent the error that we had initially, where, you know, if you don't randomize it, then it could ruin everything. So if we call self.randomize, not only will randomize still work, or it should still work, because it resets self.data, but, you know, now it'll initialize everything, and then we'll all be fine. So we call self.randomize in a function, and that erases most of the problems that I was telling you about, where I can go to should I go. If we remove the randomize function right here, it just breaks everything. Anyways, let's get back into it. We should be able to go through this second section pretty quickly. We've already done the randomize, so the next functions are going to be quite short and kind of miscellaneous. Like, they're going to do a bunch of stuff that is useful but probably not required. So we're going to define the init name, which will take the names coming in, the names coming out, and then we're going to iterate real quick over the in, and then we're going to go and go through all the data and give the names. That's about it. It's about as complicated as it gets, and then we're going to repeat the same thing but just change the data to -1, and we're going to iterate over the out in. So really simple, just assigning names. And then next we're going to do a little show of self, which is going to, if you recall, it's just going to print some stuff out. For deep, you don't really need this, but if you want like deep insights on your data and how it's being changed. This is what I used, and you could use it as well if you do plan on making any changes to the program, which I highly recommend. Like, try to make this thing more efficient. Absolutely. Like, even I'll admit, there's tons of improvements. I mean, I just made that self.randomized improvement. So, yeah, there's a lot of stuff you can do. And so the show is just going to iterate over the columns and the data, and then over the nodes and the columns, which those should be rows. I mean, they could be columns. I visualize them as rows, the layers. And then we're going to do a p-show, which is going to be very similar. So what we're going to start off by doing is enumerating over self.data, starting at 1. That way all this stuff is a little easier to read. Now we're going to use our color library to print an F string. You can really detail this however you want. I detail my stuff in little weird ways. Once again, I think this would actually be better if we put this into the repler, but I don't exactly, I mean, we can do that. That shouldn't be too hard. If you recall, the repler, it's REPR. We've taken self, and that should be about it, and we should be able to just put this into here to where we can print this dude out, and then the shell will be for more detail. But if you're going to print out a neural network, I think you're going to want to print out the pretty version, And for node tracker, node, and enumerate layer starting at 1 for ease of read. That way we don't have to deal with, everything starting at 0, which it's fine in code, but whenever you want to print out something pretty, you really don't want to do that. So we're going to do another F string, which actually I didn't properly add the colored argument for this. We want that to be cyan, or whatever color you want, really. Like, a lot of this stuff, I'm just guiding you. You can do a whole lot of, you can take this with your own liberty and do whatever. So node tracker, we want a space just to make it pretty. This is going to be blue, and then node. Alright, so I'm just going to real quick look over all of that, because it looks to be pretty good. If you recall, printing out the node will print out this. So that should all work and give us a little colorful thing that we want. And I think I feel a lot better about having that in the repler, as it's just a better way to do it, and you can actually print out the neural network. Alright, and so the next couple of things we're going to do is test and then save the networks. So for this section, test is a little bit on one of the more complicated sides. I wouldn't say it's too complicated, but I mean, whenever you break everything down, nothing is too complicated. But this is definitely a little bit more complicated than the other ones. So what we're going to do is we're going to end up creating a dictionary of expect to expect, which, if you recall, are in the form of tuples to expect, which is in the form of tuples here, which is going to be the put in and the put out. So that's what we're going to create, our little dicti. So reiterate for expected to expected in dicti dot items, which, if you don't actually know what a dictionary is in Python, it's basically usually use these curly braces right here, and you can assign something to something else, and yeah, and then you can access it like a dictionary, access its definition or whatever. So that's a dictionary. You can use like integers as well. So we iterate over the items. We're going to define a protocol equals input. This is just going to be like what we're going to print out. I believe we end up adding stuff to it. So for item in enumerate expected, we say the protocol plus equals f, an f string which allows us to include all of this nonsense, self.data of 0 of I, which is going to be the input layer, dot name, so this is where the names come into play, and then equals item. And so I believe what this is going to go and do is it's going to, we should be able to pull it up in the terminal. So this is the stuff that we're going to do. So input green equals 1. So yeah, it's going to define everything that we want. It's going to define the names right here, and then it's actually going to print the results at the bottom. So we're going to print the protocol because we're going to want to change it. So we print protocol, and then we are going to do the exact same thing for toExpected, iterating over it and printing it. There we go. It looks perfect. And then we're going to reset the protocol, and this one is going to be a little bit more complicated. So that protocol equals results, and now this is actually going to be colored. So yeah, we're going to self.forward propagate, which is basically running through the neural network. So if we go here, you have a neural network. To propagate is to move through it. Forward propagating goes through inputs to outputs. To back propagate is to fix everything by going backwards, basically. So this is a function that we will define in the next section. We're going to forward propagate expected. We're going to initialize good equal to true. For item in enumerate 2 of toExpected. We're gonna add the an f string, so protocol plus equals f self.data -1, which is the output of I dot name, and then we're gonna go and say it equals rounding, because this stuff does get quite detailed, what ends up being actually the value of that node, because we forward propagate, we're directly changing the node, so we can actually go into the data after we forward propagate and get the value. So we can go in and we can say self.data of -1 and of I dot value, and then remember we are rounding, so come around to, I'd say we round to 3. That would probably be best. And then we're gonna have to go ahead and check and see what's actually, like, how close everything is. So we're gonna do this little if statement. So if we round toExpected to 1 and we round self.data value to 1, then they should equal each other, because we want it to be close enough to where basic rounding, which that would leave it to 0.1. So we see down here a 0.9. If that 0.9 is rounded up to 1, like that's what we want. We want, if go equals 1, we want the result to end up being above 0.95, which is what this makes sure of. So it's going to set good equal to false, and then if good, we're going to print this whole thing in green. If not good, we're going to print it in red. This enumerates, and so we're going to get all of this stuff in either green or red. And the good thing about this is that it can go through everything, and if you have a lot of outputs, it's going to go through everything and check, and if even one thing is wrong, it's going to print it in red. But if everything's good, it'll print it in green. So really useful. This was one of the more complicated parts. Congratulations, you just did that. I will say the next section is by far the hardest, but also the coolest. So just stick with me. We're going to define 2 functions which aren't necessary, but kind of necessary for this as a library at least. So what you're going to do is with open of slash stored networks slash file name dot pickle comma wb as file, and then what we're going to do is pickle dot dump self dot data into that file. I recommend writing the explicit storage area, because if you don't, then if you run your program in different sections, like if you run it from neural networks, it's going to store it somewhere different than if you run it from test, and you don't want that to happen. So I recommend just writing the explicit space that you want to store all this stuff in. So yeah, pickle dot dump self dot data into the file. And now why am I using pickle? That way I do not have to worry about explicitly extracting the data from the list and turning it into a CSV or whatever. Like, I just don't want to have to deal with that. So I just use pickle, because remember, the data is in classes. So it's just a lot easier if you do that. And then to load, all you do self.data equals pickle.load file. It's that simple. Yeah, that's really cool and really simple, and I love that part of it. You know, pickle is very useful if you're trying to save everything with an AI. It's kind of important that you save your AI, like especially if you want to keep on training it. Like, you're going to want to save it somewhere. You don't want to just keep your computer open. And without this, you would have to restart your program if you end up running it and it doesn't produce what you want, and you can't even use your AI if you don't save it somewhere. Because, like, you have to remember that to use an AI, you have to forward propagate it. So just saying, oh, I train it and it works, won't be good enough. You have to save it. That way you can actually do stuff to it. Alright, this next section is section 3. I call it the takeover. I call it the takeover just because it gets complicated, and this is the actual learning stuff. So we're going to define functions, random learn, update, backpropagate, sigmoid, and forward propagate. Alright, like the way this looks. See, there might be another function in there, learn, but I don't know. We'll start with the random learn, which is going to be what you call whenever you want to train your thingy. We take the input to expect, we set strictness equal to 0.01, just how strict we are on what we want and how close everything should be whenever we end up printing it. Repeat equals 1000, which is how many times we're going to iterate. Learning equals 0.01, and then show equals false. Alright, so now if the length of the input doesn't equal the length of the output, that's a problem. So that's the first thing we should, make sure is situated. So we're just gonna raise value error. I know this isn't the way you're supposed to do it, but this is the way I'm gonna do it. So error input to output is unmatched, and we'll write this in red to make sure we scare the user as much as possible. There we go. Value error. I just got to get that out of the way. Don't want something bad like that happening. Alright, so length of equals length of input. And now we're going to iterate over in range, repeat. And for reference, you want to use, like right here, whenever you're iterating over range, it's best practice, like technically it's programming. You can do whatever you want. It's best practice to use underscore if you're not going to use the underscore, and you don't need to read it. But otherwise, you want to use I initially. If you have one, like a number line, but if you have a grid, the next one you would use is J. I don't know what you would use after that. I mean, I guess you could go down the alphabet. So you could use like K, I think. I mean, that's probably wouldn't be bad. So you would use underscore if you're not going to use it, then I, then J, then K. But this is going to be underscore because we're just iterating, doing all of this, as much as possible. So the chosen is going to equal a rand int because we want the random. We want to choose random stuff. Eventually, it's all going to even out. Like, especially having 3, that really doesn't matter. But whenever you have bigger data sets, you want it to be random. Like, you don't want to just iterate through everything. And hopefully, ideally, when you're training, you're able to programmatically create a data set larger than the amount of times you're going to train your model. That just makes everything better. There's other ways to do that. Like, you can eliminate nodes in a process that's called, I don't know what it's called. But basically, you run it, and then you eliminate like half the nodes and try to make sure it still works. And that usually makes sure you don't overfit your model to your data, which I think is pretty cool. Especially whenever you can then, once you finally train your model, you can cut it down to like half of its size, maybe even less, and it would still work. So that's pretty cool. So we self.learn the input of chosen to expect of chosen, and then we'll just pass in learning, show, and strict. So yeah, the random learn just does the random part of it. The learn part is actually what's going to do it. You see, I broke this all down, do a whole lot of functions, and it makes my life and hopefully your life a whole lot more easier, because now you're going to define learn, which is kind of long, but not as long as it could be if I tried cramming this all into one big function. Self, expected, to expect, learning, show, and strict. And now, in terms of all of this nonsense, it's going to be broken up into 3 parts. The learn part. At least you forward, propagate, back propagate, update, do it all over again. And in this case, we do print out the results somewhere in between. So we're going to start off by self.forward, propagating. Once again, if I spelled this wrong, I'll catch it later. Expected, and then we calculate our error equals self.data of -1 of I dot value, and we'll minus to expect of I for I and range length of to expect. Alright, so this is another one of my long things. I'm a little my brain doesn't do stuff in the same way. So like sometimes I love breaking it up into something like this, and sometimes I love putting it into one thing like this. So I hope you learn from this is that there's two different ways to iterate over things, and you can actually compact it quite nicely using a list format. So this creates a list of errors, basically, iterating over length of to expect. And now we're going to do something quite similar to actually what we did in the test, where we have a protocol. So for I in range of length to expect, if we're showing things, then we will set protocol. We're going to initialize protocol to true, and we're going to initialize good to true, and then we're going to iterate. It's very similar. The only difference now is that we're going to specify the strictness. So I mean, you can probably copy and paste this a lot from the test and just make a couple of tiny changes. So for I item and enumerate to expect, we set the protocol equal to name equals the data rounded. Very similar. Do the round, make sure everything is close enough to satisfy whatever. Then if so, we set good equal to false if it's not equal. And then, I mean, this part I'm going to copy and paste it. You could do whatever you want with this, really, because this is for you. All this printing stuff, it's for you, the user, to read. If you have a better way of doing it, do it. I'm just printing this all in green or in red. Very similar to last time. But as it's moving fast, you want everything to be green and everything to be red, just that way you can see the changes easier. And then all we do, you can actually collapse this, and this will give you a better overview of the whole process going on here, because we're then going to self.back propagate, taking the self.error, which we're basically going to pass in backwards into the function, which is also why it's a lot easier if you have a node which has both its parents and its children's weight. It just makes this whole process easier. And then we're going to self.update with learning. So these functions are not defined yet. Those are the next steps in this whole thing. I'm actually going to go ahead and remove the strict that I had added. I do see how strict can actually be a little bit useful, but for y'all, it's just simpler if we remove it. But yeah, so those are the next functions. I believe once we define that, this will be done. So y'all have made a lot of progress. I'm really pumped to finish this up with y'all. Okay, and with everything all set up, there's just a couple of little blocks we need to put into place to get everything working properly. One of these is just a simple function. So this is going to be one of the more simpler functions called sigmoid. If x is greater than 100, we return 1. And the reason why we're doing this is because sometimes the x will end up equaling like a whole lot of numbers. And if we try to do any mathematical operations on it, it will completely break. So elif x is less than negative 100, we return 0, because sigmoid is supposed to average out everything between 1 and 0. And then otherwise, we're actually going to do the sigmoid function, where we return 1 over 1 plus math.exp of negative x. And now exp is e, which is the natural log. Yeah, if you didn't know what e is, ln uses base e. It's some mathematical thing, I think. I don't know. Anyways, you don't need to know what this actually does. It works. I'll show you real quick the sigmoid function. And if you look at it right here, it's 1 over 1 e to the negative z. And it creates this kind of nice slope between negative numbers and positive numbers, which is really useful for us whenever we calculate the final values. That way, if it's negative, it'll be 0. If it's positive, it'll be close to 1. And so that's what we're trying to get at whenever we're doing that. Okay, so yeah. After we do the sigmoid function, we can use it in the forward propagation. I'm going to try to define these sequentially. So we'll start with forward propagate. And we just gotta hope that we spelled all this stuff right. It just takes a self input. We'll iterate for I, since and enumerate input. By the way, enumerate, such a useful function. I'm really glad I learned about it. I wish I learned about it earlier than I actually did. Anyways, we're going to go in and forward propagate through all the weights. And this is kind of a pain, so we're going to assign sensed, which if y'all need to see the assign function, it should be in our node class. Just sets the value. So yeah, it's not that complicated. We're going to assign sensed. I don't know why it's not highlighting, for layer, and then we're going to iterate over all the other stuff. In range, starting at 1, length of self.param -1, and then for node in self.data of layer. There we go. We iterate over the data. And then we're going to initialize a total equal to 0, because now we have to, for parent number, weight, basically going to iterate over all of the parents and all the weights and stuff being passed into that node. Like if you want to try your best to visualize it. I'm not going to go into too deep of an explanation because I believe I've already done a hopefully good enough job earlier, and I don't want this to run on for too long. So for node and self.data, node.parents, we're going to add to the total, which will be the weight times, what we're then going to do is go in and find the value from the previous thing. So self.data of layer -1. Keep on going through all these lists of parent number dot value. Now this is a logical mess, but just know that it works. And then we're going to finally total plus equals node.bias. And then we will node.sig assign self.sigmoid of the total. So actually, I'll simplify this for all of y'all. That should work. There's a lot of stuff that should work, but don't worry, I won't show y'all any of the debugging process. I'll show y'all anything we need to fix at the end of the video, which hopefully is nothing, and then we'll run it and get all this stuff working. So we have forward propagate, sigmoid. Guess what comes next? Correct. The backward propagate. So back propagate. It's really going to be very much similar to what we just did. Now, some interesting things is that I find it easy to simply reverse everything, and we basically do the exact same thing. So that just makes it all a lot easier. So we're going to reverse it initially and then unreverse it. You go for count, since, and enumerate expected. Now, of course, there are going to be some differences because forward propagation and back propagation are very different in what you're trying to accomplish. So we're going to hide rather than assign, and we're going to do the sensed. And then for count in range, now going over through the hidden layers, length of self dot param -1 for second count, enumerate self dot data count -1, and now we're going to do a similar total to what we have already done. And we've basically seen a lot of this, so it's just going to be a little bit different. We're going to for count node in nodes dot parents, and we're going to get the gradient this time. It's going to be the weight times self dot data, because we're trying to calculate how much of an impact all this stuff actually has. So yeah, and then we do self dot data of count of second count dot hide total, which I will say I don't like the wording I use for this, specifically the hide, because it takes that, sets the error, and then adjusts the gradient. That way we can keep on passing everything down longer down the line, but it calculates the error, and the error is going to be what allows us to finally fix it, which is why we have that fix function right there. And that's all going to be in update, because guess what? We just finished back propagate. See, whenever you break everything down, it makes it all a lot simpler. So we'll define update and see what that takes in. It's obviously self, and then we'll do learning, and for, because this is where learning actually comes into play, for count in range 1 length self dot data. So we're skipping the input layer because the biases of the input layer are determined by other stuff, and it doesn't have any parent weights to change. We iterate over the layer, iterate over the parent weights, and then we're going to say x equals parent minus self.data count -1, which means we're going back the layer, parent index dot value, and now we use the node.gradient, and then times learning. So the gradient is going to tell you how much of an effect you want everything to have, and then the learning is going to tell you how much you want to change it based off of stuff, because too high values will create very extremes that you do not want to have, and too little values will make sure nothing changes. So choosing the proper learning value is kind of important, but not that hard to figure out by just messing around with your neural network. And then after that, we node new parents dot append x, because I don't want to change the parents because I don't know, all that nonsense. I want to make sure, because I believe we do have to go through all this stuff and apply it to the children, which is why we want to maintain original parents, original stuff, and just create new things that we can update once we make sure we're not going to ruin everything by going in and changing stuff. Alright, and then for count in range, once again we're going to go 1 to length of self.data, and then we're going to iterate over the node index node. I mean, it's just like it's literally this if you want to copy and paste it. And then it's literally basically this except for the children. So you can copy and paste that, and child index change and enumerate node dot new parents. And now we're going to finally update the children. That way the forward propagation will work properly as well as the back propagation. Self.data count -1 child index dot new children dot append the change. So we update the parents, and then we go in and we apply the parents to the children properly. And now we're going to, we're going to use our fancy little letters. For I in self.data, for j in I, j.fix based on learning, which let me see if that actually does need learning to be passed in. So yeah, self.bias. So to update the bias, we do have to change all that, because we update the weights, not in the node class, but to update the bias. Yeah, we fix it, set everything right, set everything proper, and now this should all work. I am seeing an error, not an error per se, but a notification. Oh, there it is. You don't need the strict. That's about it. Alright. And since the video lib is next to the simplify lib, we can actually test this very easily by simply changing the file that we import. And we're going to make sure that all of this functions properly. So we have our nodes, our C nodes, and a neural network. So we get a should I go. We're going to switch this to from video lib import dun dun. And now we're going to do Python of should I go. Yeah. So one little error. Remember how we made p-show? We removed it. Well, now we can do this really cool thing where we simply print out the network. I really hope this works, because I think that is very cool. Did I p-show it earlier? Yes, I did. I also removed the sleep, so I hope. So if you would like to see this network in action, please go to the beginning of the video. Okay, so actually one small issue whenever we do this, you're not supposed to print stuff in the repler. This is actually kind of interesting. So we go into node. It has a very simple return of a string. So the problem is that is not a string. So maybe we should go back and define it to show of self. You see, using the colored, I believed colored will print only a certain area, different colors. So it's hard to like kind of string that all together. So I'm going to try to keep that at show, and maybe it should be p-show. this could actually be the print. So if you define the print thing of self for the normal show, then we can return all our data since it doesn't have color. But we're going to do this a lot easier. We'll set return, and for that we're going to return .append, no .data, boom, and then return. So that should work as our REPR, however you're supposed to pronounce that. So we go back to simplified lib. It's kind of crazy that the printing is the only thing that's gone wrong yet. So a little excited about that. You do have pshow, which we can change to normal show, network.show, print network, network.show. I do know that this is supposed to be network.show, but we're just going to keep it like that. So make sure that works. The string, of course, has nothing append. That should have been obvious. Rather than append, you use plus equals for a string. And let's see if we can get all this to work. So yeah, the zipped is supposed to go around the expect and to expect. So we go to video lib 109. Is that right here? Yes. It even highlighted it for us. This is supposed to be in parentheses because the zip is what makes the dictionary. And we have more errors. Self.date. Should be self.data. Let's see. And parent number has no attribute value. Okay, so this one is another silly mistake. We just go into parent number. It's supposed to be the iterator, and I guess I forgot to close that off. And fingers crossed, it looks good. So we have our print working, our pshow, our test. The only thing left to test would really be the saving, which I can do pretty quickly because one of the good things about this is that it's really easy to actually save all this. We go to network dot, let's see, is it SaveNet? And it takes a file name, yay. And so if we actually run this, it should do all the stuff. Save the network. Where did it save? Should be in store networks, yay.pickle. It is showing up. Okay, so we need to put in the put out. So we just delete all of this now. We have our put in, our put out, network.test, and it takes in the expect, which I believe is put in and put out. And this hopefully will work. There we go. So it loaded the network, and then it did the test. It needs apparently the parameters because I don't think I stored it in the pickle file. Would have probably been smart too. There's definitely improvements you can make on this, but I hope you had fun making this. I had fun making this. I'm gonna be honest with y'all. I made this at like the start of my journey into programming, and this really got me going. I spent like about a month, just trying everything, because AI, it seems kind of intuitive. Like you go forward and back, but then you actually try to implement it and you run into a whole lot of problems. And yeah, I was spent a while struggling to get this working. I'm glad I got it working. And to get it for y'all, I spent not too long actually, but simplifying it. If we go to our final file, it's 216 lines of code. You can easily simplify it and have it still function to do whatever you want it to do. Because I kind of built this as almost like a library. I don't know how to turn this into a library, but it could be. Like, I use it you see me using it in a different file. I use it as a library, and I think it's cool. I hope you had fun. Go check out some of my other videos. Um, Comment down below what you want me to like do next, because I do all sorts of stuff. If it's like code, math, I'm into all that. Like and sub, because I'll probably drop more tutorials soon, as well as some other fun stuff. I'll see you on the next one.